the International Space Science Institute in Bern. And it is my great pleasure to welcome today Felix Landerer. Felix is a research scientist at JPL, the Jet Propulsion Laboratory in Pasadena, California, where he uses space geodesy techniques to study the Earth's energy budget and the global water cycle, in particular water storage on land, that is the changing amount of water in rivers, lakes, and underground aquifers. Felix is also studying sea level rise and ocean currents, as well as melting of the Greenland and Antarctica ice sheet in response to global warming. Among his favorite space techniques, let's quote satellite altimetry and especially space gravimetry from the GRACE and GRACE-Following mission developed jointly by NASA and the German Space Agency. Felix is currently project scientist of the GRACE-Following mission launched in 2018, the successor of GRACE launched in 2002. And before being a project scientist of GRACE-Following, Felix was also a deputy project scientist of the first GRACE mission. These two missions are dedicated to monitor mass redistribution at the Earth's surface in a changing climate and inside the Earth as a result of internal dynamics of planet Earth. And the result of this revolutionary GRACE mission will be the topic of Felix's lecture today. And I think that the concept of game changer perfectly applies to GRACE, as we will see. Felix has published many articles on mass redistribution in the Earth system based on GRACE and other techniques. He contributed to the IPCC 5th assessment report and is currently government reviewer of the current IPCC 6th assessment report. He received several awards for his work, in particular from NASA and JPL, and also from the Max Planck Society. So, Felix, we are now listening to you, and you can start your presentation.
Okay, thank you, Annie, for this very kind and generous introduction. Certainly a great pleasure to be here, and I see a lot of friends and familiar faces that are dialed in right now. So good morning or good afternoon, good evening, depending wherever you are at. So in the next 45 minutes or so, I'd like to give you an overview, like Annie said, about the GRACE and GRACE-Following missions and what they have yielded in terms of results for Earth science. You see a picture here on the first slide of the two GRACE follow-on satellites that are currently orbiting Earth. And what I'd like to do in this talk is step through the evolution of how we have measured mass change on our Earth system and dive into the technology a little bit, and then obviously spend quite a bit of time, particularly in the second half in the talk, on the results and the insights that we have gained. I started listing people that have contributed to this work, and I quickly realized I would run out of space and certainly forget to admit people because there are just so many, obviously over nearly 2 decades now for GRACE and GRACE-Follow-on. So, you know, I just want to point out here that GRACE was a joint partnership between NASA and DLR, the German space agency. GRACE-Follow-on, again, is a partnership between NASA and GFZ in Potsdam. And we're partnering with the Space Center for Space Research at the University of Texas. And we're also collaborating with the Goddard Space Flight Center. So there are many, many, many people, hundreds of people involved in the mission, in the daily operations. And then obviously we have a very large user base. So it's really thanks to these people that these two missions have yielded such a tremendous return for Earth science. Before I go into the details of the mission, I want to step kind of way out and just kind of cover some basics and appreciate that we are truly a unique place here on Earth in the sense that our planet is different than all the other planets really that we know so far, most of the other planets. And if it weren't for the fact that we had an atmosphere around us and water on our planet, our average temperature would be around minus 18 degrees Celsius. And we'd pretty much be a frozen place. And it's only thanks to the existence of water and the existence of our atmosphere and water vapor in the atmosphere in particular that we essentially have a heat blanket that keeps us at a relatively comfortable 16 degrees Celsius on average. Obviously, we have seasons, but the average temperature on Earth is around 16 degrees. We have been running an experiment as humans by essentially increasing the thickness of this heat blanket around Earth by putting greenhouse gases into the atmosphere. The source of these greenhouse gases, as you all know, is mostly fossil fuel, carbon-based fuels. And so the increase of, in particular, atmospheric CO2 is currently leading to a temperature increase. And projections are that by the year 2100, which is only 80 years from now, our mean Earth temperature could have risen by up to 4 degrees or maybe even more, around 17 to 20 degrees. Depends on how many greenhouse gases we will still emit and what the actual climate sensitivity is of the Earth system. But the point being is that we're running an experiment here, and we should really understand the implications of that. If you look at Earth, a little bit more zoomed in here, same picture, it's the blue planet. It's blue because of all the water that we have. We're almost an ocean planet because 70% of our surface is covered with water. We have beautiful clouds, water vapor, which are part of that heat blanket. But as prevalent as the water is, if you just look at the surface, if you actually pile up all this water into its volume, if you gather all the water on Earth, you end up with an amount that fits into this sphere, and you quickly realize that there isn't that much water. Most of this is, of course, ocean water, saline water. You see another blob here, which is the freshwater content of Earth. And there's another very small blob right here where my laser pointer is. It might be hard to see for you at home, but this is all the liquid fresh water that's near the surface. So in rivers and lakes or in the very surface that is accessible to humans. So this amount is tiny, but this is the amount that sustains life on our planet essentially by being cycled through the ecosystem. So the point of this is that this is a really, really precious resource. I'm trying to, play this movie here. Again, most of the water is saline, not fit for consumption. Only a small percentage, less than 3%, is fresh water. And of that, most of that water is locked up currently in glaciers and ice caps, which are dwindling, but still most of it is locked up there. And only a very small percentage of the fresh water, again, is accessible to us humans. And as we're warming the planet, we can certainly expect that the distribution and availability of fresh water in particular is changing with ramifications on how we go about our daily lives. So this is just a little bit for backdrop. If you think about how water exists, in particular fresh water, where we live, we have, of course, groundwater. It exists in glaciers and ice sheets. I mentioned oceans. We have snow in the winter. There is obviously the absence of water during dry periods or droughts. And there is moisture in the soil in the top few centimeters or meters, depending on where you are. So, the question here is, and that I'm going to address a little bit, is how this changing climate is impacting Earth's water distribution. And in particular, I'm going to show a few applications why we care. Another element of this concept of water distribution is that the different stores of water that I just highlighted in the previous slide, soil moisture, ice sheets, snow, groundwater, are not isolated. They're linked together through the Earth's water cycle. We constantly cycle water through our Earth system. Water evaporates over the oceans, gets transported through the atmosphere over continents where it precipitates either as rain or snow, and then slowly makes its way back into the ocean. So this is a coupled system, a cycle. There are timescales associated with each of these stores. Ice sheets obviously have a rather long time scale. Near the surface, it's fast. As you go deeper into the soil and into groundwater, the timescales get longer. And the magnitudes of these water cycles are actually quite astonishing. If you just take this up arrow here, the evaporation over Earth's ocean, if you only were to evaporate water for 1 year and you wouldn't have this down arrow, the precipitation, it would be over 1 meter of sea level equivalent. That's how much water is evaporated. We never see that 1 meter of sea level drop over the course of 1 year, the annual cycle, because most of it immediately precipitates, or it evaporates somewhere, but at the same time, it precipitates somewhere else. So it's balanced, but it's very energetic and being cycled. So as the atmosphere and our climate is perturbed, so are these arrows. And in that way, they also impact the stores of water. And we want to understand how big these changes are. How are our ice sheets changing? How is our groundwater changing as we change the water cycle, as we, of course, tap more into groundwater, and as we build infrastructure that is calibrated to how much water we have at any given place or moment in time. And if you think about how to measure this kind of thing, if you want to measure something at the surface, for example, soil moisture, we saw a presentation on SMOS a couple of weeks ago. You would probably exploit some radiometric properties of water near the surface. It's more difficult for groundwater, obviously, because it's hard to penetrate into the ground from high up, from a satellite altitude, for example. The radiometric properties of snow are different than that of water. So an instrument that can track holistically or all the water stores should exploit a property that's common to all these water stores. And one of those properties is mass. Each of these components, regardless of what their state is, whether it's liquid or frozen or whether it's actually visible, has mass. And if you want to track mass, you use the force. It's the force of gravity that is a common property to track this. And here's just a little cartoon of Newton, who discovered or formulated the law of gravity by allegedly being hit by an apple as he was sitting in his yard contemplating this in the late 17th century. Probably didn't happen quite like this, but the point is that there's a very simple law, the law of gravity, that any mass or any two masses are attracted to each other by the means of gravity. So if we translate this concept into a satellite, you can think of any satellite essentially as a free-falling object orbiting Earth. And this was realized first in the late 60s, early 70s with the so-called satellite laser ranging instruments that are very perfect spheres, very symmetric, orbiting Earth. And as they orbit Earth, they can be tracked from a network of ground stations with laser pulses. And from the travel times and other geometric measurements, one can deduce the force field and gravity field that has acted on these essentially free-falling objects. One is, of course, in this setup here, limited to the distribution of ground stations. And as our planet is covered mostly by oceans, that distribution is very uneven and skewed towards land areas. So with this technique, you only get a very large-scale measurement of the gravity field. It's very hard to observe groundwater at small spatial scales or a particular ice sheet or glacier with this measurement. You get a large-scale sense of how Earth's gravity is being shaped, but in order to get higher spatial resolution, one needs better homogeneous coverage and also a more precise measurement of the perturbation of the orbit of a satellite. And in fact, you know, as these SLR satellites kind of went up, people immediately started to think about how to improve that measurement. And one of the first papers that describes the concepts that we nowadays use for GRACE and GRACE follow-on was actually published in 1969. So that's over half a century ago by this fellow here named Milo Wolf at MIT. And he published a paper in JGR, which is just 4 or 5 pages, very short, essentially summarizing already the entire concept of GRACE and GRACE follow-on. So I'm just going to read this here. It says, it is possible to easily measure variations of intensity of Earth's gravity field by orbiting 2 geometrically identical satellites spaced about 200 kilometers apart and equipped to measure their relative velocity. Relative velocity meaning relative to each other. So not any more tracked to the ground, but velocity variations relative to each other. And in the paper, he goes through just a few equations. They're very basic, and just has a few figures in this paper relating the change of the potential, the Earth's potential, to the satellite velocity as it goes along the orbit. So this is an orbit here of about 3,000 kilometers, one arc, if you will. And these 2 satellites experience these kind of velocity changes. And you see that they're not the same because they're at any given moment in time, they're spaced apart. They are acted upon by a slightly different gravity field, and their relative velocity is thus different. So if you have a way to measure that, you can essentially back out the gravity change that has acted on them, and in turn interpret the mass change that has led to that gravity change. Pretty amazingly, in this paper in 1969, he also describes other applications. He says the simplicity of this method lends itself to a similar type of gravimetric survey of the moon and other planets. Well, you know, some 40 plus years later, this was actually flown. Took that long to actually build the technology to put this idea that he put forth into reality. And the GRAIL mission that operated 3 years applied this concept around the moon and mapped the moon. And it could fly very low because the moon has no atmosphere. But it's pretty cool that, you know, someone in the late 60s already thought about all this. And in the paper actually also mentions some technologies to do this inter-satellite ranging. And he says, well, this should be pretty easy to do with a laser. So, you know, and only now with GRACE follow-on have we been actually able to build that technology to realize that. So, you know, how do we get here where we are today, measuring mass changes with GRACE and GRACE follow-on? There are many sort of, or there's an evolution of technology and principles. I mentioned the SLR satellites. We also had another satellite, CHAMP, that was flown by GFZ. And that was a first time application really where a satellite had an accelerometer and measuring its orbit with GPS. So it was linking up to GPS satellites that are above it. And in that way, it was essentially using the satellite itself as the instrument in orbit, and using the accelerometers to measure non-gravitational forces, and then measuring the range variations to GPS to infer large-scale mass change. But the spatial scales were limited to 2,000 kilometers and larger. Then in 2009, GOCHE or GHOST was launched by ESA, Also a satellite dedicated to measuring gravity. In this case, though, not the change of gravity over time, but the static gravity field, and with the goal to map that to very high and at that point unprecedented detail, spatial resolution. So GOES is just a single satellite, and it goes about inferring gravity slightly differently by using gradiometers. But I've mentioned it here just to show that there's an evolution of satellite techniques exploiting essentially orbit perturbations to infer gravity. And then, of course, subject of this talk, we have the sequence of the GRACE and GRACE follow-on satellites. GRACE launched in 2002, operated for over 15 years. And these are now twin satellites, so two satellites, putting that concept described by Milo Wolf in '69 into reality and doing inter-satellite ranging. And with that technique, we get down to spatial resolutions of about 300 kilometers. GRACE follow-on then was launched about a year after GRACE had its end of mission in 2018. And it's essentially the same concept as GRACE, and I'll explain that in a little bit more detail in just a second. Using a very similar platform, because the focus here was on continuity as GRACE, with upgrades to the technology and also flying technology demonstrations. GRACE follow-on was launched on the Falcon 9 SpaceX rocket. And since this seminar is about game changers, this was a bit of a game changer for NASA, because this was one of the first Earth science missions being launched on a non-NASA vehicle, right? On a private space industry rocket. And in particular, this was launched on what SpaceX at that point called a flight-proven rocket. So that's just a fancy word for a used rocket, because it had flown before. And in fact, you can see this kind of dark patch here, which is really just exhaust dirt from the previous launch, from the second stage when that goes off. And at that point, SpaceX didn't clean these rockets or didn't paint over them. It was quite an interesting experience to collaborate here with SpaceX and to make sure that we were convinced that this works. And we're of course nervous about our payload, which is up here. And it worked in the end. It was a beautiful launch in May 2018. The payload up here that I mentioned is also kind of a game changer, in that not only is this a used rocket, but it is essentially what we call a ride share. So we partnered with private industry to essentially split the cost of the launch. In this fairing up here is also, there's a stack. I think our GRACE follow-on satellites are on top. And below that are 5 or 7, I forget the exact number, Iridium satellites that were launched at the same time. So they, of course, needed to go to a different orbit. So it's kind of like you share a taxi or a cab with your friends. You split the costs. You each, go to a different place. So we did that. It was very successful, and could serve as a template for future launches to bring down costs in particular. Like I mentioned, there's a big team behind GRACE follow-on operating the mission. You can see a picture here of the sort of the core science data system team, comprised of people from JPL, GFZ, and CSR, and also Goddard. But there are many more that are not on this picture, and it's really thanks to these people that we can do what we do, and in particular in these challenging times of COVID, where we're forced to work from home. I want to just highlight that the mission operations in the last year have been very smooth. Everyone teleworking, but it's been a good experience, and I'm very thankful for having such a dedicated group of people to work with here. So let me talk a little bit about the the concept and how we actually go about measuring gravity. As I mentioned, GRACE Follow-On is a system of 2 satellites orbiting the Earth at an altitude of just under 500 kilometers. They're spaced about 200 kilometers apart, and they're constantly measuring the range variations as they orbit Earth. You can see one satellite here being pulled ahead a little bit, accelerating, the other one catching up. We do these range variation measurements with 2 techniques currently. The wavy line here is a microwave interferometer. We also measure this with a laser interferometer, which is a technology demonstration. It's the first in space really laser interferometer ever flown. So with these measurements, as we orbit Earth, we can infer these mass changes on a monthly basis that are highlighted here just for the first year of GRACE measurements. You can see the movement, the ups and downs. Red colors indicate a decrease in mass and blue colors indicate an increase in mass. And I'll go into more detail about the magnitudes and amplitudes, but I wanted to stick for a second here with the actual instruments on the satellites and just how amazing this technology really is. So we have the so-called K-band ranging, which is the microwave instrument, the laser interferometer, which is the technology demonstration. There's an accelerometer here in the very center. You actually can't see the instrument because it's covered by others. There's star cameras to measure constantly the attitude and provide a reference frame for the satellites. We have a GPS antenna on top for the orbit determination. And we also do GPS occultation. So this is slicing through the atmosphere and inferring the distribution of temperature and humidity for weather forecasting. So this measurement is not related to the gravity and mass change measurements, but because we are at relatively low altitude, just 500 kilometers, we get a pretty low grazing angle through the atmosphere. So there's a signal of opportunity that is of high value to weather forecasting. This is just a schematic. If you look at the actual satellite, you see that it's really chock full of instruments. And the dimensions here are, it's about 3 meters long or so. So it's like a small car. It's turned on its side. We're looking at the top of the satellite without the hood or the cover. So this would be covered by solar panels. The front of the satellite is on the left. You can see these 2 baffles here, which is where the laser light enters the satellite. And there are mirrors here. It gets turned around, gets sent back around, and ranges to the other satellite, which would be about 200 kilometers to the left, rotated by 180 degrees facing each other. There are 2 tanks here that are visible. We have a cold gas propulsion system for attitude control. But other than that, we're not managing our orbit. The satellites are pointed to each other so they can do their relative measurement all the time, but other than that, they're free falling. You can see the microwave instrument here, these copper tubes. This bluish square or rectangle is one of the up-facing star cameras. The other ones are pointing to the side here. We have 3 star cameras, which is an upgrade from GRACE, where we only had 2. So this allows us really precise attitude determination all the time. But you can see, this is really kind of stuffed to its limits. Each satellite weighs about 600 kilograms or 650. And yeah, it's pretty cool to just kind of, as a scientist during the integration of satellites, I had the chance to stand next to the instrument that would then later fly. And it's really nice to have that connection and be able to understand the measurement system, because for GRACE and GRACE Follow-On, the point is, or a very important point to understand, is that the satellite itself is the measurement system, because we are tracking the free falling satellite all the time, centered around this accelerometer in the middle here. It's the entire system working together. The satellite is the instrument. So I mentioned the orbit altitude, just under 500 kilometers, the relative positioning 200 kilometers apart. We are in a polar orbit, and at that altitude, we get about 15 revolutions per day. So after 15 days, and in a good scenario, we get a coverage like this. And after 1 month, we have pretty dense coverage of the entire Earth. This does change, of course, a little bit depending on the orbit altitude. But with data density or data collection of 1 month, we're then able to map the Earth's gravity field for that particular month. And if you do that here, this is here shown for GRACE data for August 2006, it looks like this. And if you do it again for September 2006, it looks like that. And you would be hard pressed here to see any differences, because the biggest part of the gravity field is, of course, static or constant. It's not changing over time. It's due to the distribution of solid mass, if you will, on Earth, due to tectonics and the distribution of mountain ranges. You see the Andes, you see subduction zones, you see the Mid-Atlantic Ridge. So these things obviously don't change from 1 month to the next. But if you do the difference map, it looks like this. All these static features disappear, and instead you start to see differences over the Amazon in this particular example here. And you have to zoom in by a factor of about 1 million to actually see that variation in the gravity field. And this is really due here from August to September, red colors indicating a decrease in the strength of the gravity field, and thus a mass loss. And this is due to the seasonal change in the Amazon River basin as we go from the wet period into the dry period. So from August to September, the rains start to subside, to stop, and the water that is in the basin tends to drain and run off through the Amazon River into the Atlantic, and you're left with a mass anomaly, a negative mass anomaly in this basin. So we do this month over month, and then we can get a very detailed, accurate picture of how mass is being constantly redistributed on our planet. And here is the entire data record for GRACE and GRACE follow-on. You can't see much detail here, but I just want to show how much data we have amassed by now. We have over 180, going 190 monthly maps over almost 20 years. And one of the first few discoveries that were made were actually watching the seasonal cycle and the amplitude of the seasonal cycle of Earth's hydrology, like I described in the previous slide. And this kind of information is quite useful to also calibrate and tune climate models. Older models of coupled climate models in CMIP3 here had a big dispersion in terms of the annual cycle. This is shown for the Mississippi River Basin. Newer models are doing much better. So this is where this information comes in. The real or one major value of this record is, of course, the long-term variations that we're now able to see on going almost 20 years. And we're seeing massive shifts in mass, in particular related to the depletion of ice mass on Earth's ice sheets, Greenland and Antarctica, but also over land, shown here for the case of California, where the red colors indicate a mass loss due to a severe drought and in response to that additional groundwater pumping. The value of the mass change observable is really high because it maps into many components of our climate system. I highlighted that at the beginning. It's sea level, it's groundwater, but it's also related to river discharge, water use, glaciers, ice caps. All these things can be observed, or we can use the observations from GRACE and GRACE follow-on to build knowledge for these kind of variables in our Earth system. And it's due to that GRACE and GRACE follow-on are one of the most prolific Earth science missions in terms of publications. To date, we have tracked about 4,700 publications that use the data either from GRACE or GRACE follow-on. in the next, or maybe in the remaining 15 or 20 minutes or so of my talk, I want to step through a couple of the science highlights that the missions have returned and are still returning, and highlight the utility of the measurement. This was a paper by my colleague Matt Rodell and many others published 3 years ago, kind of highlighting the long-term trends in our mass redistribution on Earth, in particular over land, related to hydrology. So I already mentioned the ice sheets here, red colors indicating a strong decline. So Antarctica along the periphery in particular, Greenland, Antarctica, but we're also tracking massive depletion related to groundwater pumping in the Middle East, in Northwest India. We're seeing interesting features that are man-made. We see the Three Gorges dam filling, right, as an increase here in China, as that massive lake was slowly filled. We see natural variations. We know that climate is not the same from one year to the next. So we see recoveries from previous drought periods over the Amazon basin. We see increases here of water in Africa. So an increase of water is good in the sense of water availability, but if there's too much of it, of course, we have flooding issues to contend with. So just understanding the magnitude of all these changes is providing vital insights into how our Earth system is developing or evolving. So this here is an animation of the Greenland mass loss over time over the almost 20 years of GRACE and GRACE follow-on. And as you can see, what essentially happens is a progressively redder Greenland, indicating mass loss, in particular along the periphery. And it might be hard for you to see here at home, but there are the flow lines are overlaid. The flow lines of the ice are overlaid of the mass sheet here, ice sheet here, as mass changes, in particular on the outlet glaciers, where you see a concentration of mass loss. So my colleague Josh Willis, actually at the beginning of the series, highlighted this a little bit more, that we're seeing this mass loss in particular along the periphery, and in particular where the ice meets the ocean. So at the ice-ocean interface, what seems to be occurring is that warmer ocean waters here trigger a mass change that's concentrated here. Glaciers melt, and the ice sheet behind it tends to flow faster, and it's not being replenished. So it's out of balance and losing net mass. Greenland overall has lost about 280 gigatons every year over the last 20 years or so. And if you just, it's a gigaton is a typical unit we use to track these mass changes. And just 1 gigaton of water, if you place that on downtown Manhattan, it would look like this. So we have about 280 of these every year from Greenland alone that are disappearing. And 1 gigaton here fills about 400,000 Olympic swimming pools. So staggering mass quantities. Want to highlight just a little bit more on the findings. I mean, there's the overall long-term decline, but it's also quite interesting to look at the individual years, because we know that the mass change and the mass loss in particular is not constant over time. There are years of much larger mass loss, like here in 2012, but there are also years where it seems to level out. So the first GRACE follow-on data that came in 2018 indicated that we were above the long-term extrapolated mass change. And indeed, the summer of 2018 was very cold in Greenland. And then in 2019, though, this precipitously dropped again. Greenland was in a state of melt because it was very, very warm, and a rapid drop. In fact, the biggest drop ever, certainly in this data record, occurred 2 years ago in that summer melt period. And if you look at the surface temperatures around Greenland in 2017 and 18, you see that it was relatively cold, in particular on the eastern side. So this was where I mentioned this ice-ocean interface and the rapid mass loss and the outlet glaciers. Seems like relatively cold ocean waters were at least temporarily able to slow the mass loss on the western side. And then in 2019, however, we had massive warming again, This is just surface temperature, but there are other measurements from probes taken in the water here that indicate that the whole water column warmed and led to an acceleration of this ice sheet. My colleague Ingo Saskin at AVI in Germany has taken this GRACE data record and extended it back to the 1950s or so, and mapped the balance between the seasonal accumulation, because it always snows in the winter on Greenland, and the seasonal meltwater and discharge. And what we find is that, in particular in the last 2 decades, Greenland is increasingly out of balance. Almost all years since 2000 or so see an out of balance mass loss, and 2019 was indeed one of the strongest mass loss periods. So more melts every year than is being replenished in the winter. A similar picture is emerging over Antarctica. This animation here again shows the mass loss from GRACE and GRACE follow-on over that 20-year record. And you see the mass changes again concentrated here on the western side, West Antarctica, in particular Pine and Thwaites glaciers. Interestingly, we see a slight increase here on the Eastern Arctic side in terms of mass. They're very muted colors relative to the mass loss on the western side. So the net is still very negative. But before GRACE and GRACE follow-on, we didn't really have much knowledge on how the Antarctic ice sheet would change as a whole in a warming climate. Many early climate models in particular hypothesized that an increased, more vigorous water cycle would lead to more precipitation on the ice sheet. And since it's still cold in Antarctica, this would lead to a net accumulation. So this seems to pan out on the eastern side, but what was not taken into account, in particular in the early models, was the ice-ocean interaction again, which seems to play a crucial role here for the net melt on the western side. And that net melt is far outweighing the increase we see on the eastern side. Okay, I want to switch gears, going from ice to aquifers. GRACE and GRACE follow-on are helping us to map the state and health of the large global aquifers which are mapped here. And the study in 2015 or so by my colleague Jay Falmietti found that out of the 37 largest aquifers on Earth, 21 are in a state of stress. They're being pumped unsustainably. And that, of course, has big ramifications for food security or security as a whole. Here is just 2 images from the Office of the Director of National Intelligence in the US, mapping stressed water stressed regions in 2012, and then a forecast from that time period into the mid-2020s. And you see an increased stress over those, or many of those aquifer regions. And if you overlaid a map here of where we currently have crises or wars, this correlates actually pretty well with where we have long-term continued water stress, because the lack of water just propagates into lack of food and stressed societies in general. So again, this just points out to the vital value of knowing how we're using aquifer water sustainably. But it's not just really these crisis regions that are experiencing water stress. In 2018 and 2019, actually, Europe experienced severe droughts, and this was tracked by GRACE and GRACE follow-on. And I think many people in Europe had not experienced water stress like that before, which in some regions actually led to the rationing of water, or at a minimum, severe impact of daily life. Shipping routes were closed, and crops didn't produce the expected return. So the notion here that water stress only occurs in maybe near the tropics or in deserts, I think we need to change that notion as our climate continues to shift towards warmer temperatures. And the value of GRACE and GRACE follow-on comes in because we can not just measure the water at the surface, but we measure the entire water column. We get the full depth. And what was seen here is that even though towards 2019, 2020, much of the surface water had recovered, the drought was actually kind of baked in deeper into the soil and into the groundwater, such that the net mass deficit, even in late or early 2020, is still way below where it ever was in the entire 20 years previously. So we now have tools to do a better integration of the GRACE and GRACE follow-on measurements for operational drought monitoring. I'm just showing one here, which is the drought monitor on the US side, which outputs on a weekly basis these drought indicators using, among other things, GRACE and GRACE follow-on data. And the nice thing that they are able to do with this tool is that they assimilate the data and are able to disaggregate it in depth. So this shows the surface layer here in the in the African basin, the root zone, and then into the groundwater. So we have the satellite measurements that now inform us on these large spatial scales, and we're really able to make this information available and for local or at least regional water managers and incorporate that into decision making. And you will also see here that the surface changes are much faster and the groundwater is much slower and a little bit lagged in response relative to what's happening at the surface. But knowing what's going on deep below is really vital for designing your water systems, designing your infrastructure, and making decisions, water allocations. And these things map into a lot of other things, such as the overall ecosystem health. And they also map into the carbon cycle and the carbon balance. There's a lot of research, in particular in the last year, coming out, linking the water cycle with the carbon cycle, because they're so tightly coupled. Lastly, I'm gonna check my time here. Okay, just a few minutes highlighting another application. So I showed you ice, I showed you some hydrology applications. I don't want to neglect the oceans, because GRACE, in conjunction with other observing systems, provides some crucial information as our oceans are changing as well. Josh Willis at the beginning of this series talked about the altimeters measuring the height of the ocean surface. GRACE follow-on is very complementary because it gives us the mass of the ocean, that mass change. And obviously a mass change, if we put more mass in, the sea level will go up, but sea level also goes up if it expands because of ocean warming or because of salinity changes. This is what we call a steric change. So this is a density related change. And the sum of these should match the total sea level change as measured by altimeters. So there's a powerful concept here, which we call the sea level budget, where you can solve this equation for either one of these terms, or you can just check for the balance. You can solve it for the residuals, which is an interesting thing to do. Josh also showed this curve here, the altimeter record over going 3 decades now, showing an increase and an acceleration of sea level rise, actually on the order of 3 to 4 millimeters per year. The ocean mass component in this sea level rise is about 2/3, right? So this is the ice melt from Greenland and Antarctica and from glaciers that I showed you previously. The difference here implies an ocean warming and expansion. So we can use this difference to infer a net heat uptake rate of the ocean, and that currently contributes about 1/3 to the sea level budget. If we look at the sources of these mass changes, all of these plots here have the same vertical range of a little bit over 9 millimeters. So Greenland is clearly a major contributor, but glaciers, so glaciers in the Andes, in the Himalayas, in Europe, are also a major source, similar to Greenland, to the net ocean mass gain over the last 2 decades. The Antarctic ice sheet, a little bit less so, but maybe at a more increasing rate. This plot here actually ends in 2017. If we had extended this to 2020, you would see an uptick again here, even for Antarctica. Terrestrial water storage, so this is all the non-frozen water that's not in glaciers or ice sheets. No net change really over the long term, but a lot of interannual variability. You see, for example, here, this big downswing in 2011. And that was in fact related to a massive shift of La Nina and the Indian Ocean dipole, leading to massive precipitation over the Australian continent. And it was so large that was actually reflected in the global sea level budget, that we saw a drop in global sea level just because precipitation had, for a period of time, shifted such that a lot of water rained over Australia. And it's largely in so-called endorheic basin, where the water is very slow to drain off through river networks. And most of it, as you can see here, is kind of caught in these puddles. They need to evaporate. So that time scale is slower, right? So you get this net effect, at least over a period of time, where it needs time to make its way back into the water cycle and be available for ocean mass gain. And if we just look at the sea level budget again, since 2005, the total here is the black curve by altimetry. And the orange here is what is contributed by the net mass gain as observed by GRACE and GRACE follow-on. And the green is the warming. We have measurements from these hydrographic floats that are distributed around the global ocean that track temperature changes, but only down to 2,000 meters. The mean ocean depth is actually 4,000 meters. So this only captures about half the ocean volume, the upper half. If we sum the green and the orange, it should come out to the black. So the blue here is the sum of the green and the orange. It doesn't quite get there. We have a slight residual, in particular in the last years, an uptick in the residual. So one of the things that we're investigating right now, and it's pretty hot topic in the sea level budget community, is whether this might indicate a deep warming that's below 2,000 meters that we're just not tracking with the observing system, but which we could infer from this, or whether this indicates maybe a measurement uncertainty. The answer is probably it's a little bit of everything in here, but this is really vital to know for our overall planetary energy imbalance. Just the oceans are the major reservoir for this extra heat that we're gaining because we have wrapped this blanket around Earth. So where this heat goes and whether it ends up in the deep ocean is of crucial importance to understand where we might end up in terms of our net global warming in 50 or 100 years. I think in the interest of time, I'm just going to skip this plot here real quick and kind of wrap it up and leave some time for questions. I framed my presentation and talk today here mostly in terms of surface mass change related to the redistribution of water in the water cycle. I want to make sure that I also point out that the solid Earth itself also undergoes mass changes that then are obviously visible to the satellites as a gravity change. And there's a lot of applications emerging from GRACE and GRACE follow-on that exploit that data record to learn more about the interior of the Earth. For example, we see large earthquakes like the Sumatra earthquake or the Tohoku earthquake in Japan, where not only can we observe the co-seismic, but also the post-seismic process deep in the crust and the lithosphere and the upper mantle, where we see post-seismic gravity changes on the order of, or on timescales of decades, long after the earthquake has happened, where the mantle and the lithosphere are still adjusting. So it's a very powerful measurement here to inform our knowledge about the Earth structure and how that works. That's the same thing for glacial isostatic adjustment. So this is the rebound of the Earth from previous ice sheets in the last ice age. The ice sheets are long gone, but the crust still has that memory and is rising, and it has a gravity signal associated with that. I want to kind of wrap up here with kind of zoom out again. Where do we go from here? So we've had the GRACE and GRACE follow-on measurements, very successful missions, In fact, the utility of these measurements has been recognized in many white papers and many reports. And I'm going to just highlight one here in particular, the decadal survey from NASA, published in 2017, that kind of provides a roadmap for the next 10 years or so. What should we observe? And mass change has been labeled as one of the 5 most important observations to acquire in the next decade. And that's really due to the utility of the measurement, like I showed you with all the examples. And currently we're exploring, there's a dedicated group studying how to implement next missions and what technologies to use. I didn't speak to this much here in this talk, but the laser ranging interferometer is a powerful new technology because it tracks the relative variation in distance between the satellites to much better precision and accuracy than the microwave, by the factor 10. And if we are able to change our mission design, maybe include a second pair, upgrade the other instruments on the satellite, we can also exploit this improved precision for a high resolution gravity field, both in space and time. Right, so this speaks here, the second point here speaks to that we're targeting constellations of maybe multiple pairs to work with. And in particular, one thing that has been highlighted is to seek out international partnerships. So there is collaboration going on with ESA, with DLR, with GFZ, to find the best solution here. Of course, also a cost-effective solution to go forward and continue this vital data record, and in particular, try to not have any gaps as we go from Grace Follow-on to the future. Maybe zooming out even a little bit further, because I think this is the last talk in this Game Changer seminar series, at least for Earth science. So, over the last couple weeks or 2 months or so, saw a lot of presentations highlighting the value brought about by specific missions, the altimeters, SMOS, air quality. Here's just an animation of, I think, mostly NASA missions, or NASA plays a role. There are many more from our partners in ESA and other space agencies. And the point is really that we're living in an age where we have a massive amount of observations available. And I think that's really the game-changing part of all of this, that all this information is coming together, and is no single mission here is the silver bullet. It's everything working together that enables us to provide information that has value to society. It's obviously very interesting to scientists to just learn more about how our Earth system works. And another game-changing part is that this huge amount of data is nowadays literally available at our fingertips, and at everyone's fingertips. Everyone has a handheld device, and we have these apps now where the data that we generate just a month later or so, we have processed everything, is available for you to scroll through your phone. I think there are similar apps available from other providers. NASA has an app, just a plug here, for Earth Now. But this is really a game-changing part, I think, also where kids can literally just with a click of a button here look at the latest gravity field or map of ozone or sea level, and I think that's really cool. We have a tool here to engage people that are not experts, but people that are really interested, and those people are actually funding our work, right? So I think this is really a game-changing part. Also for the satellite data in this day and age. So I think that's it. Sorry if I went over time a little bit, but thank you very much for your attention, and there might be some time for question, hopefully.
Thank you very much, Felix, for this beautiful lecture. You have already several questions in the chat, and I think you will have many more, and the participants can either write their question in the chat or raise their hand, and they will be allowed to talk. So maybe you could start answering the question already visible in the chat. Do you see it, or do you want me to?
Yes,
Okay.
I have I have the chat. I can start near the
And
top.
okay, so if
Okay,
you
so
can just remind the question in order
yes,
that participants
I'll read the question. So I need, yeah, there are more coming in, so I need to scroll a little bit here.
Okay.
So from Jason Durr, let's start there. Is it possible to see time variations in release of mass from hydrothermal vents or melting of ice caps? So hydrothermal vents, I think that would be too small and too localized. Our footprint, if you will, our spatial resolution with Grace Fallen is on the order of 300 kilometers. We can push this down a little bit with some processing tricks, but hydrothermal vents, I'm not aware of anyone having looked at that, but my first guess would be that's too small. So melting of ice caps, I think I spoke to that. The answer is obviously yes. That's one of the biggest signals we see. Oh yeah, okay, you say disregard then. Okay, well, it's hard for me here because the questions just keep pushing up. Okay, here's another. Was the recovery of surface water, root zone, and groundwater just from GRACE data, or did you need other complementary data? So this is the disaggregation video that I showed. This is run by my colleague Matt Rodell. So this is a hydrology model that assimilates data, and it assimilates other data than GRACE. It assimilates precipitation data. It assimilates, I believe, also soil moisture data from probably SMAP or SMOS. So it's not only GRACE, but GRACE is vital to provide a constraint on the overall water budget in that column. Okay, how does GRACE distinguish between surface, root, deep, groundwater? Okay, I just kind of spoke to that. So GRACE alone cannot distinguish between where in the column the mass change originates from. You need other ancillary or complementary information. And that's kind of what I spoke to last, that it's really the combination of these various observations that is so powerful in understanding how our Earth system works and the evolution of the water cycle. Okay, let's see here.
There is a question about the estimate of moment of inertia. Do you see it?
I don't see that.
So the question is, have this data been used to estimate changes in moment of inertia?
I believe so. Yes, there are studies that use the GRACE data in particular in conjunction with other data, from SLR to study that. Yes. So the answer is yes. What GRACE and GRACE follow-on provide us is the origin of the mass change and where it goes. So you can certainly compute the moment of inertia and trace it back to the particular process and event that is impacting inertia changes. Not sure if that answers the question, but.
So there is another question. I don't know if you see it. The question is, what is the minimum detectable water mass per footprint?
Yeah, okay. That's a good question. I didn't really speak to that. So I said the spatial resolution is about 300 kilometers in the current setup of single pairs. The accuracy at that scale, 300 kilometers, is about 1 centimeter of water height. So if you think of a big pool with sort of a spatial scale of 300 kilometers, if you fill that with to a depth of 10 millimeters of water, we would be able to detect that and resolve that. As you go to larger spatial scales, the sensitivity and accuracy improves and gets smaller.
The next question is, I lost it. It was about the new direction for the future. You talk about that, but if you can comment again.
Yeah, so there's from Glennis.
Yes.
I hope I pronounced that correctly. What are the directions for refining the technique? For example, having multiple altitudes would give you some sort of vertical information, but perhaps that's not so valuable to you. So we're, in particular for the next mass change missions, where there are many concepts and ideas, and it's a multi-dimensional trade space. So the things that impact the resolution most is, one would obviously be to lower the altitude of the satellites. We want to get closer to the source, because the gravity or the potential field strength goes off with, or gravity field strength with 1 over r squared, right? So as you get closer, you have more sensitivity. If you get lower down, you also increase things like atmospheric drag, which are not related to gravity, but which would impact the intersatellite range, which we need to correct for. So that's a trade space. We can vary the separation between the satellites. We can, there are technologies to fly drag free. Ghost or Goche flew much lower, 250 kilometers or so. I don't know the exact numbers, but there are people here that know. So if you know, you can put that in the chat. There are also concepts that use multiple pairs. Grace Cristolon are in near polar orbit. If we have an inclined orbit at maybe 70 degrees or so, we would get better observations on the east-west direction, which would help us to reduce some of the ambiguities we have with just one line of sight measurement. So these are the things that are being studied. There are also more complicated orbits, pendulums, or cartwheels, which I don't really have the time nor the expertise, frankly, at this point to explain in more detail. But the point is that any change in the mission design also needs to take into account the satellite as a system, right? Because the satellite itself is the instrument. So everything you change or improve needs to match the other technology that's on the satellite, you know, the accelerometer precision, the ranging precision, the precision of the star cameras or the GPS needs to be considered as a whole, as a system.
Thank you. There is a question from Roger Bonnet. He raised his hand. So, Willy, can you allow him to talk?
Hello?
Hello?
Yes, I can hear you.
Okay. You may not know me. I have been the director of science at ESA for 18 years, and I have introduced space science in Earth, of the Earth in EC. So I've been a director of EC. Well, my question is very simple.
Nice to meet you.
My very simple and maybe naive. Do we have the possibility to measure how much water is evaporating from the Earth?
You mean as a net mass loss?
Yes. That, in other words, when will the Earth become the second Venus solar system?
Yeah, that is a good question. It's a simple question. The simple questions are the hardest to answer. I don't know. It's an interesting question. I would need to think about more about this to. I mean, I'm sure there is a way to measure this. I'm not sure that the gravity changes that I talked about here and the measurement concept of intersatellite ranging would allow us to do that. I mean, it would imply a sort of degree zero, if you think in spherical harmonics, gravity coefficients, mass change, which since our satellites orbit the center of Earth always, you know, we're not sensitive to that. I don't know. it's a great question.
But
Thank you.
if I may, just
Please.
a quick comment. My understanding is that since about 1 billion years, the amount of water on Earth is more or less constant. So, including water vapor in the atmosphere, in the ocean, and so on. So,
Yeah,
I don't know.
Glenn is in the chat, has a good comment, which I think is
okay.
probably the right way, where you do lunar laser ranging. So you reference to another point that's outside of the Earth system.
Yeah.
Obviously, the Moon-Earth distance is constantly changing due to other processes too, like tidal friction. But maybe one can back that out. Maybe if I may answer just one more question, something that might be useful for people to understand, and I didn't talk to that, is by Leonie. What is used as a reference gravity level for groundwater storage in order to detect anomalies? So that's a great question. I didn't really explain that. We don't use a gravity reference level as such, an absolute level. We can detect changes over time. So we typically pick a mean period over which we have observed. Let's say a common period is 2005 to 2010. We just take that as the mean field and compute all the gravity changes relative to that. So what these measurements that I described here can yield us very accurately is the change over time. But for example, for an aquifer, I can tell you how many cubic meters, how many gigatons the California aquifer has been depleted over the last decade. I cannot tell you how much water is still left. I don't have an absolute measurement. I can only measure the change. And the reference level in that sense is arbitrary, but the relative change, right, a trend will always be the same regardless of the reference level. I hope that answers that question a little bit.
Okay. So I don't know if there are other questions. If not, I have one. Can you comment a little about the performance of the laser interferometry system?
Yes, of course. So I didn't spend much time here in this talk on that. That could be a whole separate talk. So this laser interferometer, it's depicted here. The wavelength of the laser is actually in the invisible, so you wouldn't see it. But it's a technology demonstration on Gray's follow-on, and it's performing really well. It measures the range variations to a factor 10 or 30, depends a little bit on the frequency, better than the microwave system. That doesn't translate into a 10 or 30 times better gravity field, because there are other limiting factors, other error sources that contribute to the act, or that determine the noise floor in our mass change or gravity field. But the experience on orbit has been very well. As an instrument, it's working very smoothly. The requirements in terms of pointing are very tight for a laser, because the beam width, as the laser light travels 200 kilometers to point to the other satellite, is much smaller than the microwave. The microwave is much broader and has thus less tight requirements on the relative pointing of the satellites. So there were initially questions on whether we could even acquire a laser link over such a large distance, 200 kilometers. That turned out to be not an issue at all. The system and the pointing works really well. And we have obtained now continuously the measurements of the laser ranging data, and are looking into that, analyzing it concurrently with the microwave data. Obviously, there is a big team of engineers looking at the data, since it's a technology demonstration, to learn lessons for when we might want to fly this as a primary instrument. We're also doing just starting to do new science with this laser ranging data, trying to exploit this improved accuracy in new creative ways. will probably not improve the accuracy on a monthly gravity field, but we're already seeing that maybe there's sub-monthly information in here where the microwave is just too noisy that we could exploit from the laser ranging instrument. So overall, it's just been a very positive experience operationally, and the data looks fantastic.
Okay, thank you. We have two more questions, and then I think we close the session. One is about the gap between GRACE and GRACE follow-on. So the question is this a significant problem? And we have another question from Jean Benveniste. And the question is, what and how much knowledge brings the combination of GRACE and GOCE?
Okay, yeah. So the first question, the whether the gap was a problem. So we have about 11-month gap between GRACE and GRACE follow-on. Obviously, we were blind to massive or mass changes in the Earth system during that time period. Certainly to the same capability as GRACE and GRACE follow-on provide. You know, it is a gap in terms of all the systems that assimilate data. The drought forecasting, of course, didn't have the GRACE data available at that point anymore. I'm not sure how much it then started to slowly deviate or drift away from the actual data, but you know, we didn't know for a whole year how the ice sheets are changing, and we saw when GRACE follow-on came in that it was offset from the long-term trend, and certainly would have been interesting to look at how 2017 played out when the ice sheet started to go from a fast state of melt to a slowdown, and where exactly those mass changes started to slow down. In terms of intermission calibration, maybe the question is geared towards that a little bit. GRACE and GRACE follow-on are what we call inherently calibration free. The same is not true for the altimeters that Josh described, where you really want to have overlap. So we're confident that we don't have bias issues between the missions. Of course, it's always really nice to have overlap and to be sure of that. But from first principles, I don't think we have inherent intermission calibration issues. That is probably also true here because the mission design for GRACE follow-on is built so strongly on GRACE heritage that we have a good sense of how sensitive these satellites are with respect to temperature changes or other geometric factors. So, you know, with a grain of salt, there is no intermission bias issue. I'm sure we would have learned interesting things had we had overlap, even for just a few weeks or a month.
Okay, so
and then
the last question is GRACE and GOCE.
That's a good question. I think that's only now starting to be exploited, where I haven't seen any studies that actually combine GRACE follow-on data in particular with GOCE. Of course, GRACE and GOCE have been combined to yield really the best static gravity field in particular. GRACE tends to do really good in the longer wavelengths, the large scale features. GOCE provides a lot of information where GRACE is not sensitive at the higher spectrum, so the small scale features. And in combination, the sum of both provides us the best gravity field. And Jerome, as you know very well, you know, that has a lot of useful applications to detect ocean currents, to remove a mean marine gravity field, applications like that. So very powerful together. And I would say the sum is more than its individual parts.
Okay, so you have two more questions, and then I think we stop. So if you can give quick answers.
Okay, wavelength of the
the
laser, the wavelength of the laser is over is I think 1020 something nanometers or so, and why 200 kilometer separation of the twin satellites is so specific. So we kind of have a band of variations. We let the satellites drift between 170 and 270 kilometers over time, over long time periods. They can freely drift. Right now, Grace Fallon is at about 180 something, I believe, or 190 or so. That has to do with the wavelength also of the features that we want to resolve at the surface of the Earth. So you can kind of take the separation distance needs to match, if you will, somewhat the altitude, and or not match, but be consistent with. And the separation distance then is if we're too far apart, let me put it that way, we wouldn't be able to sense small scale features on the Earth, right? If you have two glaciers sitting next to each other, maybe each 300 kilometers, if we're too far apart with our satellites, they would just appear as one to us. But if we're closer together, and this is kind of the sweet spot between 170 and 270, we are then sensitive to certain mass changes on the ground. And
Okay.
I'll leave it at that.
Thank you very much. So I think it's time to close. Thanks again, Felix, for this very interesting lecture. Beautiful, wonderful. And thanks to all participants. I would like to remind you that we will have another lecture in Earth Science just in 1 month. It will be on the CFO-SAT mission that measure waves and surface winds. So rendezvous in 1 month. But next week, there will be other lecture on other topics. So bye-bye to all of you, and thanks again, Felix.
Thank you for tuning in. Great to see so many people here.